Hello everyone, I am Sahil Sawant, currently pursuing my MTech in Computer Engineering at VJTI Mumbai with a background in Electronics and Telecommunication Engineering from VIT Pune. Over the past few years, I have worked on radio telescopes, RF signal chains, astronomical data analysis, Bayesian modeling, and SDR based systems. And through all of this, one thing kept appearing everywhere, that is the signals. In radio astronomy, in embedded systems, AI, communication systems, signals are literally everywhere. But the problem is, most students study signals as equations. Today, we are starting differently. Today's question is, what is signal? Like, really, what the signals are? In textbooks, we will read a signal is a function of one or more independent variables. Mathematically, it is correct, but practically, it is incomplete because when we reduce signals to equations immediately, we miss its real meaning. Now, let's take a step back. A signal is not just mathematics, a signal is variation that carries information. And let me say it again, a signal is variation that carries information. Not just variation, not just numbers, but variation that means something. Now let's look at the real world examples. For example, a microphone. When we speak, air pressure changes. The microphone converts that air pressure variation into voltage variation. The voltage variation here is the signal that is being carried forward. In ECG machine, your heart generates electrical impulses. The ECG captures the voltage that changes over time. That waveform which is being generated is the signal. In radio communication, an FM station transmits the electromagnetic waves. Your receiver captures the field variation which were sent through transmitter. That change in field strength here is the signal that we are capturing. In astronomy at Ayuka, when we observe the radio solar bursts, we are measuring tiny fluctuations in electromagnetic radiation. Those fluctuations are the signals from the sun. Signals are not just classroom ideas, they are the language that define physics. Now we formulate it again. A signal is a measurable physical quantity that varies with time or space and carries the information forward. Key part here are measurable, physical, and varies and carries information. If it doesn't carry information, it's just noise, which we will be talking in later episodes as well. Let's categorize this intuitively. Continuous signals and discrete signals. Continuous signals are analog voltages from microphone. Discrete signals are sampled digital audio files. Examples: deterministic and random. If the signal is a pure sine wave, it is deterministic signal. Thermal noise is example of random signal. Periodic and non-periodic. AC power signal that was being generated was periodic signal, whereas speech which is being generated is non-periodic signal. Notice something, we haven't written a single heavy equation yet, and yet you already understand signals more clearly than most of exam prepared students. Why are signals so important? Because every engineering system does one of these three things: generate signals, modifies signals, and extracts information from the signals. A filter modifies the signal, a transmitter generates the signal, and a receiver extracts the information from the signal. Even machine learning, it processes signals just in vector forms. Signal processing is the foundation layer beneath communication, AI control systems, RF, and biomedical engineering, everything. Imagine this, you record your voice, look at the waveform. What are you actually seeing? You are seeing the air pressure that changes, converted to voltage, sampled into numbers, and it is being stored digitally. That waveform is a compressed story of your vocal words. Signals are physical events translated into measurable forms. That's powerful, right? If you remember one thing from this lecture, let it be this: a signal is not an equation, it is physics captured in measurable variation. Fourier transforms, filters, sampling, these are just tools. The signal itself it's the reality that is being recorded. In the next episode, we will answer a deeper question. If signals are variations over time, why do engineers move to frequency domain? Why do we break the signals into sine waves? Why does the Fourier exist? And that's where things really get interesting. If you are serious about understanding signals and not just about passing examination, stay with this series. Welcome to Signals and Stars.